Hi everybody, welcome back to the Feynman technique. Um, Today we are going to take a look at this integral, which is a modified version of an integral on the channel Maths 505. His integral was like this. I'm going to be evaluating this. So that's the integral from 0 to pi over 2 of the natural log of sine x and all of that over 1 plus sine squared x dx. All right, so how are we going to solve this? I think a lot of people just starting Feynman integration might go ahead and try this, making a function of t that's equal to this. That doesn't lead anywhere really good. Of course, we can recover our original integral I by letting t equal 1, but we can't get a good value for anything else. Like if you try to evaluate that at t is equal to 0, you end up getting negative infinity on top. So that's not going to work very well. So first, we're going to transform this integral using a substitution. And the substitution we're going to make is u is equal to tangent x. That might seem strange since we don't have a tangent x here. Another one I tried earlier was u is equal to sine x, which makes a little bit of sense at first because you have a sine x here, but don't forget, you'll just end up getting back that u, and you won't really be able to work with that. We need something, we need like a constant plus a function inside our natural log. So to get that, what we're going to do is let u equal tangent x. And you'll see what happens. So if u is equal to tangent x, well, let's, of course, this is going to imply that du is equal to secant squared x dx. So cosine squared u du is equal to, dx. Cosine squared x du is equal to dx. So now we have to figure out what cosine is. Well, given that u is the tangent of x, that would mean its opposite side is u, its adjacent side is 1, and its hypotenuse would be the square root of 1 plus u squared. 1 plus x squared. So using the cosine identity adjacent over hypotenuse, that is going to give us that cosine of x is equal to, let's see, 1 over the square root of u squared plus 1. All right. And then if we square both sides, we just get that cosine squared x is 1 over u squared plus 1. So we'll copy this here. And there is our dx in terms of u and du. All right. So now let's figure out what sine is. Of course, that's just going to be u over the square root of u squared plus 1. All right, let's perform the substitution. So now I is equal to, let's see, u is tangent x, so u is tangent pi over 2. That goes to infinity. And tangent 0 is just 0. All right, sine x is this. This might not look better yet, but it's going to work. And then, of course, sine squared x is just u squared divided by u squared plus 1. And our dx just becomes this. All right, so you see we have the same values for I. So the substitution was performed correctly and validly. So now let's clean this up a little bit. All right, you see we can distribute this u squared plus 1 into the denominator. So let's do that. That's going to cancel this. And then we're just going to get a plus. What did we have? Sorry. Okay. Okay, so yeah, we're going to get a u squared plus 1, and then this. So that's just 2u squared plus 1. Okay. Well, that doesn't look much better, but let's go ahead and split this into two separate integrals. So we're going to get something plus something else. Using the properties of logarithms, we can write this whole natural log right here as just the natural log of u minus 1/2 natural log u squared plus 1. So u squared plus 1, and then we'll bring the 1/2 outside. And then in here, we're just going to have natural log u. All right, what did I do wrong? Plus. There we go. Minus. There we go. Okie dokie. So now let's label these two integrals. We'll label this one, well, just this part, and we'll label this one. Okay. So we're going to say that the integral from 0 to infinity of natural log u over 2u squared plus 1 du, that is just going to be equal to I1 is what we'll call it. And then we'll call I2 equal to this integral, equals I2. So now our original target integral is just going to be I1 minus I2 over 2. Okay, let me switch this. There we go. All right, so you can see that that lines up perfectly. Now let's go ahead and see if we can modify that, see if we can figure out what this is going to be. All right. Well, usually, if we didn't have that 2, I would know right away how to solve this integral, but we do have that 2. So let's see what we can do. Normally, the first step I would make, well, is to bring this dummy variable to x. And then I'm going to let x go to 1 over x. All right, so bringing x to 1 over x, we'll get 0 there, infinity here. This is going to become an x to the negative 2. This is going to become a natural log of 1 over x, which is just negative natural log x. And then we will have negative 1 over x squared right there. All right, so you can see our I1s are still correct. So I1 is equal to this, and it's also equal to this. Okay, let's go ahead and clean this up a little bit. This negative cancels this negative. Let's distribute this x squared in here, x squared. And this is just going to become a 2. All right, and then I'm going to switch the order of these. And then I'm going to put a negative sign here to switch the bounds of integration. All right, so there's our new I1. So we have I1 is equal to this right here. And we also have I1 being equal to this. Okay, so let's see. We have a 2u squared here. Let me zoom out a little bit. Maybe you can see more of the problem going on now. All right. So you see right here we have a 2 in front of our u squared, but right here we don't. And also this is a 2 and this is a 1. So what we're going to do is we are going to multiply x by 2 inside the integrand. That's going to give us a 4 here. But that means we have to multiply by 2 on the outside also. That's just a quick form of a substitution. I'm sure you guys can all follow that. And you'll see that we have a common factor of 2 right here. That's going to cancel the 2 outside. So Now we have I1 is this, and also I1 is this. So we can say that I1, well, hold on. Let's clean this up a little bit too. All right, so we're going to get two separate integrals. We're going to break this up into natural log x and natural log 2. All right. So let's see. Now we have I1 plus I1 is equal to our first representation for I1 plus our second representation for I1. And of course, I want to bring this dummy variable back to x. All right, that means this is 2I1. So we're going to go ahead and put a 1/2 outside. Oh, I see. There we go. Okay. So now what? Well, let's see. You'll notice that this and this are exactly the same thing. Okay? So they cancel out. And this right here is an integral that is solvable. I'm not going to solve it. I'm going to use the online integral calculator because you guys aren't here to see me integrate stuff like this. So I'm going to go ahead and plug this into the online integral calculator. And we are integrating from 0 to infinity. I should know the formula for that. I'm terrible at memorizing formulas. But anyway, this is what we get. All right, so let's just go ahead and replace that here. And you can see that's exactly the same thing. All right, this is going to make the denominator 2 to the 5/5, and we'll just have a pi natural log 2 to the 5/5 negative. All right. I'm sorry, this is not I, this is I1. All right, so we've taken care of I1. Now let's work on I2. All right, so I2 is equal to this. Okay, how are we going to solve this? Well, we could technically create f of t being equal to this. And by the way, this is not going to be solvable just directly, although you may be able to use integration by parts. I'm not sure, but that's not what we're going to do. We're going to use Feynman's technique. So we're going to create a function of t. Now, it might be tempting to put the t here, because then technically we could evaluate f at 0. That's just going to be 2 times an integral we've already solved. But we're not going to do that. We're going to put our parameter t right here. That way, f at 0 is 0. All right, so we'll state that f of 0 is equal to 0. And also, f at 1 is equal to I2. All right, now let's take the derivative with respect to t of our function of t right here using the Leibniz rule for differentiation under the integral sign, which says we can just take the derivative of this function directly by taking the derivative with respect to the parameter inside the integral sign. So taking the partial with respect to t is going to bring this whole term downstairs. And then using the chain rule, taking the derivative of the inner function, we're just going to get a u squared. All right, now just to verify I did the differentiation correctly, let's put a d dt in front of our original f of t to make sure it lines up in our graph, and it does. Okay, again, this is an integral that would be solvable. I could add 20 minutes to the video by showing you how to solve that step by step, but it's partial fraction decomposition and then arctangents. That's pretty much it. So what I'm going to do is I'm going to evaluate this using the online integral calculator. So we will plug this in to our integral calculator and we will be integrating with respect to u. It looks like I forgot to change my dummy variable. 0 to infinity, go. All right. That gives us this expression right here. Okay, so let's copy that and paste it right here. And let's see if it got it right. Yeah, it did. So there's our f prime of t. All right, well, now to get to f of t, what we have to do is integrate this. And again, that is, we have to anti-differentiate this with respect to t. And that would be doable with, you would start with the substitution, u is equal to the square root of t, and then go from there. I'm not going to do that. I'm going to, again, plug that into the integral calculator just to save time. Again, you guys are not here to see me integrate stuff like that. That's no fun. That's just busy work. All right, so this is what that turns out to be. All right, of course, plus a constant of integration. So f of t is actually equal to this. All right, plus c. Now, we have to go back up to here and say that f of 0 is equal to 0, and that's going to allow us to solve for c. Well, that's going to be equal to this thing when t is 0. So that whole expression is going to go away. This is 2 squared. We can bring out the 2. Say this is just natural log 2. Solving that equation gives us c is equal to negative 2 pi natural log 2 over square root of 2. So our f of t is now this, and it is. You can see that matches up perfectly in our graph. Let me zoom in here so you guys can see that a little bit better. Yeah. That matches up perfectly. All right, so now what was the point of creating that f of t? That was so we could say that f of 1 is I2. Well, that's going to be equal to this, of course, when t is 1. So that is I2 right there. Okay, so now, going even further back, we know that I is I1 minus I2 over 2. So our original target integral I is just equal to I1, which I will copy and paste right here. So it's this, and then minus I2 over 2. And of course, I2 is just this. There we go. Now let me copy the original integral down here, or from up here down here, and we will see that those are equivalent. Okay, and then all you'd have to do, basically, you could simplify this expression right here. I'm not going to do that because, again, you're not here to see me do that. But that actually simplifies to something much cleaner. But go ahead and do that yourself if you'd like. I'm going to leave it like that because this is the answer. Okay, guys, I hope you enjoyed that. We'll see you next time.